6.2, we're going to find tangents, areas, and arc lengths, and I don't think surface areas. Yeah, there's a little type. I don't remember ever seeing surface areas in parametric form. All right, so let's get started with the basic, finding derivatives. So let's recall that a parametric equation, a set of parametric equations is described by two equations, f and g, which at the same time are functions of t. In this case, for now and for the sake of simplicity, these functions are functions of time, right? And so if we want to find the tangent or the slope at a given point, of course, just like in calculus 1, take the derivative and evaluate it at the given point, at the given value we want to know. So the thing is, this dy dx is going to be, which ultimately is a dy dx, and that first derivative is a function of t. And that's because, both functions y and x are functions of t. So in other words, all we have to do is take the derivative of the x equation with respect to t, and take the derivative of the y equation with respect to t as well. And what do? Divide the derivative of y by the derivative of x. Okay? A curve will have horizontal tangent when the derivative in the numerator, that is, the derivative of the y equation, equals to 0, and vertical tangent when the derivative of the x equation equals to 0. In a very similar way that in calculus 1, when we found these values where the function contains horizontal tangencies and vertical tangencies. It's just that in this case, we're putting it together as a function, or rather as two equations that depend on one new variable. The second derivative is a little bit tricky. So this is what we have to do for the derivative. So we take the derivative of what we got in the first derivative with respect to t, and divide and keep dividing by the same first derivative of the x equation. If it looks a little complicated here, this will make more sense when we get to the examples. So let's do an example. Of course, the condition here is that dx dt cannot be 0, because otherwise we would be dividing by a 0, and you know the story. When we divide by 0, it's undefined, right? So we need to make sure about that. All right, so we're given the curve represented by the equations x equals t squared and y equals 3t minus 5. So they're asking us a few questions here. So they're asking us for find the slope of the curve when t equals to 2. And this is like the most straightforward case scenario, because all we have to do is simply take the derivative of the equations. That is, okay, let me write the system again. So that's x equals to t squared and y equals to 3t minus 5. This means that dx dt is just using the rules of differentiation. That's a 2t, and dy dt equals to 3. Okay? And so this means that we can define dy dx, which is dy dt rather, dy dt over dx dt. And so we know what these quantities are from the two equations. Let me just highlight them so you can. So this is dx dt. That's dx dt here. This is dy dt. That's dy dt here. And all we do, just replace whatever they correspond. So that's going to be 3 over 2t. And that's the derivative, first of all, because, well, in order to find the slope, we need the derivative. So we may now evaluate this derivative, dy dx, evaluated at t equals to 2. And all we do is simply substitute t equals to 2 wherever you see the letter t. 3 over 2 times 2, and that's 3/4. So that's the value of the slope when t equals to 2. All right? It's pretty straightforward. We have equations that depend on t. Take the derivatives with respect to t, come up with a function of t, and evaluate it at the point where t equals to 2. Now the next one, for the next one, the point 9, 4. Well, we need to be careful with this kind of questions because, well, when we find the first derivative in parametric form, that gives us a function of t, right? And in this case, they're not giving us the value of t. In this case, they're giving us a point. So before we can do anything, our job is to first figure out what is the value of t, or when is the particle at the point 9, 4. All right, it's not like the previous example. So we have a couple of parametric equations. Number one, and in this case, okay, so that's x equals t squared, and y equals to 3t minus 5. So yes, we already have an expression to find the slope because we already found the derivative in part A. We can use that same expression to find the slope at any particular time. Now, in this case, we need to know first when is the particle at the given point, that is 9, 4. So this is what we're going to do here. So what we're going to do is we are going to set each parametric equation equal to its corresponding value. For example, the x equation, set it equal to x equals to 9, and the y equation, set it equal to its y value of 9. In other words, let's rewrite the system of parametric equations. So that's 9 equals to t squared, and y, or not y, actually 4, equals to 3t minus 5. Let me just highlight this just so you can keep seeing what am I doing with this. So this is green and red. And well, we have to solve these two equations for t. All right, so on the one hand, we get that t squared, that is from the first equation, t squared equals to 9. That means t equals plus or minus 3, which is the same as saying t equals to 3 or negative 3 and 3. So we get two values for the first equation. For the second equation, 3t minus 5, set it equal to 4 in this case. Solve the linear equation, add 5 to both sides to get 3 equals to 9, and divide both sides by 3 to get t equals to 3. Now, notice when we solve this equation, or both equations, we need to look for the value of t that repeats, that it's the same on both equations, that it's common to both. In this case, well, notice the first equation gave two different values, that is negative 3 and 3. However, the one that repeats, it's the positive 3 in this case. So let me highlight that value first. So highlight the one that repeats, and in this case, that's the time when the particle is at the point 9, 4, given this set of parametric equations. So there is some sort of a shortcut, if you will, to determine the value of t given the point. And one of those, and that shortcut says to just solve the easiest of the equations. However, my advice is to solve both equations and just make sure that the same value of t appears on both in order to determine that value of t. But I mean, it's your choice. This is just, I solved both of them just to make sure that we get the same value of t. All right. And well, now that we know the value of t, we may now find the derivative dy dx at t equals to 3. And we'll recall that our derivative was a 3 over 2 times t, which in this case t equals to 3. Cancel the 3's, and the answer equals to 1/2. So the slope is 1/2 when t equals to 3. All right. So they're asking us to solve, or rather to find the second derivative. So do the second derivative with respect to x. Well, so again, this is the one that it's a little tricky. So let's see. So number one, d squared y dx squared equals to the derivative with respect to t of the already first derivative divided by dx dt. All right. Let's do one thing at a time. Well, we already know an expression for dy dx. We got that in part A of the problem. So let's just use it. Let's just substitute it in here. That equals to d dt, and that was 3 over 2t, with divided by dx dt, which is the same dx dt that we used in the first derivative. That is simply 2t. All right. Okay, so in order to differentiate this term in the numerator, well, notice the t in the denominator, we cannot take the derivative while the t is there. So d dt, notice everything, by the way, is still a function of t. Even though we have a dy dx, yes, we're looking for the change of y with respect to x, but however, in this case, it's having that t governing in the background this time. So, and everything's still in terms of t. So that's 3/2 t to the negative 1 and over 2t. And well, the derivative of this 3/2 t to the negative 1, that's negative 3/2 t to the negative 2, and divide that by 2t. Well, there's a couple of things that we need to do here. Number one, negative 3/2 divided by 2, it's the same as saying negative 3/2 times multiplying by the reciprocal of the number that we're dividing in this case. And over here, t to the negative 2 is going to go to the denominator with positive exponent, t squared times the t that we had over here. So in this case, that's going to be negative 3/4 times 1 over t cubed. Just multiply the t's and clean it up a little bit. That's a negative 3 over 4 t cubed. All right. So that's one example on how we find the derivative in parametric form, and also second derivative, and different ways to compute the slope in one case, given the value of t, which is a very straightforward problem, or knowing the point. And again, for the point, you have a couple of choices. Number one, just solve the easiest of the equations, which is fine, but if you want to make sure about both equations having the same value of t, solve the two equations and just identify the value or the values that are the same, because it could be more values. We could have, I don't know, maybe something like a cubic equation that has more solutions, or both quadratics. Maybe both solutions end up being the same. I don't know. But in this case, well, it was the case that it was only one solution. All right, that actual one solution that was common to both equations. Let's look at another example. Find dy dx and the derivative and the second derivative for the given set of parametric equations. All right. So for this one, let me rewrite this system just a little bit so you can easily say what differentiation rule am I going to use here, especially for the derivative of the x equation. So you might want to rewrite this sine squared t as sine t inside the parentheses and square it. So, and in this case, well, let's take the derivative of both equations first individually. So dx dt. So in this case, we're going to need a chain rule, right? Because we have a function inside of the parentheses raised to a power. So 2 sine t times the derivative of sine, which is cosine t, and the derivative of the y equation with respect to t, that's going to be the derivative of cosine, which happens to be negative sine. So that's out the derivative of the individual equations. So now we need to put this together into a dy dx, which again, let's write the formula again, dy dt over dx dt, where our dy dt is negative sine t over the denominator dx dt, which is 2 sine t cosine t. And check this out, although this denominator 2 sine t cosine t is actually an identity, I would leave it like this as 2 sine cosine, because if we do this, when we get to actually get the second derivative, we would get a simpler expression. So cancel the signs here. That's going to leave us with so that's a negative 1 over 2 cosine t, and we can still simplify this. Actually, we can move the cosine to the numerator using reciprocal identities, because cosine, or rather 1 over cosine, is the same as saying negative, how do I have, okay, negative 1/2 secant t. And that's our first derivatives, negative 1/2 secant t. And again, my advice is that you simplify this first derivative as much as possible, because if you had left it like this, or even used the identity negative sine t over sine 2t. So when finding the second derivative, you would have had to deal with a quotient rule, and well, you don't want to do a quotient rule inside of a big second derivative that it's also a quotient. So just keep it simple, all right? It's fine. I mean, it works to refresh our identities, but I mean, we're still using identities, but in this case, to write this in a simpler way. So that's the first derivative, and let's see what's next. Second derivative. That's the derivative of the first derivative divided by the derivative of x with respect to t. All right, so okay, what are we substituting first of all? So this negative 1/2 secant t, it's going to go over here, because that's our first derivative. All right, and dx dt, well, we already got it from the original setup. All right, so differentiate with respect to t what we got for the first derivative, negative 1/2 secant of t, divided by dx dt, which is 2 sine cosine Okay. And what else from here? All right, so from here, well, let's take the derivative of -1/2 secant t. Well, number one, the derivative of secant t is secant tangent. And so that's going to be -1/2 secant tangent. Divide that by 2 sine t cosine t. Okay, and well, yes, we're essentially done with the calculus here. That's the second derivative, but we would be expected to simplify this madness right here using these identities, all right? So number one, let's see. How are we going to use these identities here? So I'm going to rewrite tangent and secant, everything actually in terms of sines and cosines. That is, I'm going to write -1/2 divided by 2. It's the same as multiplying -1/2 times 1/2. That's going to give us a 1/4. -1/4 times, okay, so what do we have? Sine, cosine in the denominator. And this secant, I'm going to send it to the denominator as its reciprocal function, which in this case is cosine. And tangent, that is sine over cosine. Let me highlight all this so you can see what am I doing. So this secant became cosine, the one I highlighted in green, and sine over cosine, it's our tangent. All right. So let's see if we can simplify anything. So it looks like we can simplify the sines. And that's going to leave us with -1/4. Okay, it's cosine, that's cosine cubed. And we could leave it like this. However, we can still use, what's it called? Trigonometric identities. Well, 1/cosine is the same as saying secant cubed. All right. So that's another example. How do we find first derivative and second derivative? Again, when it comes to the first derivative, try to simplify as much as possible so you don't have to do a lot of work when taking the second derivative. Right? Okay, let's move on to one more example. Find the slope, the equation of the tangent line, and describe the concavity for the curve given by x equals to t squared minus t and y equals t cubed. All right. So number one, let's find the derivatives first, because well, we need all the derivatives in order to get the general first derivative. So the derivatives individually, that's 2t minus 1 and 3t squared. So, and we may now form the first derivative by dy dt over dx dt. In this case, dy dt, which is 3t squared over 2t minus 1. So that's our first derivative, given these two equations. And well, oh, by the way, I forgot to type something here. They're asking us to do everything when t equals to 2. All right, when t equals to 2. So that's our derivative. dy dx, actually. And well, let's evaluate the slope, dy dx, when t equals to 2. And all we do, again, just substitute the value of 2 whenever you see the letter t in your first derivative, that is over here. So 3 times 2 squared divided by 2 times 2 minus 1. And that's going to give us, well, in the numerator, that's 2 squared, which is 4. 4 times 3, that's 12. And 2 times 2 minus 1, that's 4 minus 1, that equals to 3. And the slope equals to 4. All right. Well, so we got the slope. They're asking us for the equation of the tangent line. Well, in order to get the equation of a line, we need 2 pieces of information. Number 1, the slope, which we already got, and a point. Well, in this case, we don't have a point. We just have the slope and one value of t. So how do we get the point? Well, we have a set of parametric equations for which for different values of t, the output is an order pair. In this case, well, we can plug in t equals to 2 here in our set of parametric equations, wherever you see the letter t, and that's going to output for us that order pair corresponding to that value, the same point that we're going to use to find the equation of the tangent line. So let's go about it. That is x of 2, y of 2, that is 2 squared minus 2 and 2 cubed. That's going to result into 4 minus 2, which is 2, and 2 cubed, which is 8. This means when t equals to 2, the particle, because again, we are considering this set of equations as a particle moving along that path, the particle is at the point at the point 2, 8. And we're going to use those 2 pieces of information, this slope here and this order pair. So using the point slope form, y minus y1 equals m times x minus x1, that is y minus y1, which is in this case 8, equals m, which is 4, times x minus x1, which is 2. And well, you know the drill for this, just multiply to distribute the 4. 4x minus 8. We can actually cancel this 8. And the equation of the line is y equals to 4x. All right? Y equals to 4x. All right. So let's see. I have an idea here, just so you can get a visual of this. Well, so what if you would like to check your results, graph everything, but the thing here is, number 1, we have a set of parametric equations, x equals to 2t squared minus t. And over here we have a rectangular equation. So if you do this using a graphing calculator, you wouldn't be able to graph these 2 together because one is in one mode, one is in parametric mode, and the second one is in rectangular mode. So in this case, how about we parameterize this line the traditional way by letting the independent variable to be the t, that is x equals to t, and y equals to 4 times x, which is 4t, and graph the 2 sets of parametric equations together. All right? So I'm going to go to the graphing calculator so we can visualize those results. So the original set, which is t squared minus t and t cubed, and what we got for the second line, okay, that was x equals to simply t and 4t, and let's graph them together. Well, for whatever reason, I need to zoom it in a little bit. Well, so we're getting this equation at when t equals to 2. So let's see if I can second calc value when t equals to 2. And oh, it looks like I need to zoom it out a little bit. Or let me do some zoom standard. Okay, so here when t equals 1, 2, notice how the red line, which is the equation of the line, it's actually tangent to that point, and it's actually tangent to the point 2, 8. So yeah, let me change the window here to a better, I'm gonna do -1 to 10, that's fine, and or -1 to 5 actually, and 1 to 10, that's fine. And here at the point where t equals, where we have the point 2, 8 right here, which is the point of tangency for so the red graph is the equation of the line, while the graph in blue is the parametric form, which in this case is y equals to t cubed. All right. I mean, again, just so you get a visual of what we are essentially doing over here. All right. And let's see.